Unless there are questions or comments from previous lectures, we're going to move on to a different topic today. We're going to start our study of cosmology.
I've got a question
yes.
About the previous topic. Since r and theta and phi and t were not good coordinates for r equals beta for the horizon, but those were still good coordinates for spacetime inside the horizon, right?
Well, in some way of saying it, firstly, you're not even sure which part of spacetime you're talking about. Like when, let's remember the Penrose diagram. It's true that if you take the you're saying take Schwarzschild coordinates, right?
Yes, yes.
It's true that if you take Schwarzschild coordinates, you get some sort of description of something, and in some sense it's both the description of this and this depending on some identifications. Okay, but Schwarzschild coordinates would lead you to believe that there's one region behind the horizon when there are actually two. You should just not trust Schwarzschild coordinates, really speaking, below the horizon. You know, because it reaches a singularity here and you have to continue beyond that. You don't really know how to continue in those coordinates. To do that, you have to move to better coordinates. Now, it's true that the real thing is some analytic continuation of what's behind the what's r less than beta. But that's, you know, it's dicey logic. As we've seen, it gives you you might think, therefore, it might lead you to a wrong result. I think, logically speaking, you should just not trust those coordinates below. This is the safest thing to do. For instance, if you wanted to describe this, you really have to use ingoing coordinates. You want to describe this, you really have to use outgoing coordinates. If you use Schwarzschild coordinates, you might not. Another way of saying it is you wouldn't know whether t was going up, whether r should go this way or that way in the future. That's what distinguishes this and this. In order to know that here, how do you do it? See, suppose, so this brings us to an important question. Suppose I've got, let's say, a vector that goes like this. Okay, a vector that points from here to a later v.
Is that a null vector?
Not necessarily. Something that goes like this, but could be null. Let's say it's null. Let's say it's an outgoing geodesic. Okay, I've got a vector like this, and I want to know which way is future. Algebraically here, it's not that clear, right? It's some vector. This way could be future, that way could be future. One way of understanding which way is future is this. Let's take it to be a null vector for this problem. You see, if I take a vector here, it's very clear that this is future. But now, there's this beautiful fact that you cannot take a vector and change it from future directed, and continuously change it from future directed to past directed, unless it becomes space-like somehow. Any null or time-like vector that is future directed, and then you move it continuously, will always stay future directed.
What does that mean mathematically? Could we quantify it more rigorously? Not that rigorous.
It means that your watch would tick going that way. I mean, okay, yeah, you probably could. You probably would have to assign a direction. You know, what you would probably want is to assign a vector field to this problem that is nowhere 0. It would probably map to, it would probably map to the following problem. Can you draw a vector field? Okay, that is continuous, null, and nowhere vanishing. Okay, if so, the arrow on that vector field will give you the arrow of the future. Okay. You know, but that makes it sound fancy. It's the same thing, right? This is the future. Now, you cannot change future to past without going through space. You understand that, right? It's intuitively clear. Right. So if you've got a non-zero vector that's pointing to the future, it's either null or time-like. And you keep varying it continuously through a smooth space, it will always point to the future. So if you're confused in some region because all your intuition has gone crazy about which way is future and which way is past, take a vector that you conjecture points towards the future. Continuously move it to where you know it points either to the future or the past and check which way it points. Okay? Now this in Schwarzschild coordinates you wouldn't be able to do because you'd have to go through the singularity, this thing that is singular. Okay? So you wouldn't really know how to deal with the inside of the black hole in Schwarzschild coordinates. And this is one, yeah. It's just dangerous to do anything in Schwarzschild coordinates inside, though you'll often get it right. For instance, for computation of curvatures, you get the right answer both for here and for here. But you wouldn't know which way, one way you were doing it for. Okay? Conceptually, it is better just to think in terms of good coordinates. Okay? Then of course, as a calculational procedure, if you can show that a calculation in good coordinates is the same as some easier calculation in Schwarzschild coordinates, as a mathematical trick you're free to use it. But conceptually, you should think in good coordinates. Formulate your question in good coordinates. And then, after you formulate it into mathematics, then your job as a physicist is done, right? I mean, then it's just tricks. Okay. Yes?
If you have a hypersurface and normal is perpendicular to it, like if you look at the span of all the vectors within this hypersurface and the normal, that would be d-dimensional.
Yes.
Like the original method.
Yes.
But
unless it's null.
Yeah. So that's not a problem.
It's not a problem. It's just the null manifolds are very special manifolds. And in fact, it's not a problem. You know, it's basically this, that suppose you considered a series of manifolds that go between being space-like and time-like. There's a discrete difference in some way between the space-like and the time-like ones. And the boundary between that is special. It's not singular as a geometrical manifold, but special properties. Let me give you one more answer. There are two things to say about this. Let me give you one answer that is actually often useful for intuition. Okay, all these things, many things I would like to tell you, but let me tell you this thing. Okay, suppose I take the metric minus dt squared, okay, 1 minus beta by r plus dr squared over 1 minus beta by r plus r squared d omega. Okay, and now I do the strange thing that quantum field theorists often like to do. I analytically continue time. Okay, I take t goes to it, or is it the other way? Is it minus I? It won't make a difference to our algebra. But let's get it right. We want minus v dt I minus I v dt to go to minus v. So we got minus I. No, plus I. Minus I, minus I. Minus I. Okay, suppose I do this procedure for whatever reason. Okay, there's often very good logic for doing this. And we can discuss this if you like. But at the moment, suppose I do this just for a moment as an experiment to see what I get. Okay, I get the manifold dt squared, dt e squared into 1 minus beta by r plus dr squared over 1 minus beta by r plus r squared d omega t squared. This is now Euclidean, 4-dimensional Euclidean manifold. There's no time. Okay. By the way, the ability to do this and get a real manifold depended on some properties of the behavior in T. If I had odd functions of T, for instance, I would have got imaginary numbers here and I wouldn't have known what I was doing. This particular case, in particular, is very simple because T is a Killing direction. T doesn't appear, so this is very nicely stationary Killing. That doesn't matter. Now let's look at this manifold. Okay. What I want you to do is to picture this manifold. So there are 4 directions. Of course, there is the sphere whose radius is r. Okay? Now, there is r, but there's also this t. Now, what happens to this t at this t direction? Okay, let's take 5 minutes to do this properly. Let's look at what happens to this t direction. This t direction has at r is equal to beta, the coefficient of dt squared goes to 0. Okay? Now this is pretty strange. You might think the point r is equal to 0 is a singularity in this manifold. But it need not be. It need not be if we do something else. Can anyone suggest what we might be able to do to make this, to make r is equal to 0 non-singular in this manifold?
R equals 0.
Oh, sorry, r equals beta. R equals 0 is terrible because it becomes non-Euclidean. We won't go past r equals 0. Sorry, r equals beta. We won't go past r equals beta. But can anyone think of what? Can anyone think of a manifold where the coefficient of something goes to 0 and yet it's not singular?
It's the sphere. Two plane in plane polar coordinates.
Both of you are right, but that's a simple example. Right? Suppose, that's very good. Suppose we look at dr squared plus r squared d theta squared. This is a two-dimensional manifold where the coefficient of d theta squared goes to 0 at r equals 0, yet it's not singular. But it's actually, if you think about it, very important for the non-singularity for the periodicity of theta to be exactly 2 pi. So when the metric is dr squared plus r squared d theta squared, if the periodicity of d theta was, let's say, less than 2 pi, what is the shape of the manifold we'd get?
Cone.
It's a cone. Very good. Okay? Can you see this? You've got this plane. You've got a plane here where theta goes from theta to 2 pi. If theta went to theta plus something else, these would be identified. And you could do that by taking a sheet of paper and folding it up into what people put chana into, that kind of thing. You understand?
But not necessarily a cone like this, could be a cone like this also.
Yeah. Up, down is no meaning here.
Right. Oh, of course.
Yeah, it's an intrinsic thing. Okay. Yeah. Now you see this manifold, actually this manifold, its curvatures are everywhere the same. And the curvatures are local quantities. You compute them without knowing what periodicities or coordinates are. But everywhere except one point, namely r equals 0, clearly a singular point. You can see that, right? So if you've got if in a two-dimensional space you've got a metric like this and r goes to 0, there's only one way to make the manifold smooth. That is to make this coordinate periodic with a given periodicity. Okay, just as a fact about manifolds. Now let's go back to this metric. In this metric, we've got a 4-dimensional manifold, but two of the dimensions are playing essentially no role because they're a sphere, and where we are worried about everything, that sphere has a fixed size. Okay, so we've got a 2-dimensional manifold made up of r and t. On each point, on top of each point of this 2-dimensional manifold is a 2-dimensional sphere. Things might get dangerous if the size of the sphere goes to 0 somewhere, but it never does. So we can forget about, for purposes of smoothness, we can forget about the 2-dimensional sphere, the S2. So though we've got the whole space, for the purpose of understanding when this is a smooth manifold, we can forget about this. So this is a 2-dimensional problem, just like the one I wrote down for you. Now, the question of whether the point r is equal to 0 is smooth or not is a local question. Okay? So what I'm going to do in order to understand whether this quantity is smooth or not, this manifold is smooth or not, this is a diversion, okay? But since it came up, let me go through it. I'll tell you how it relates to your question in a minute. Let's first understand the phenomenon. The question of whether it's smooth or not, we can understand in an expansion, in a Taylor expansion around r is equal to beta. So let's do that. Let us set r is equal to beta into 1 plus, let's say, alpha. And we'll work to first order and alpha, lowest non-trivial order and alpha. Okay? So what do we get? Well, let's look here. To lowest non-trivial order and alpha, we get dt squared into 1 so alpha. Right, the minuses cancel. Betas have also cancelled. Here what do we get? Here we get plus beta square. Okay, now beta will be unfortunate because anyway, plus beta squared into now what was this? This was alpha. And the alpha squared. Is this clear? Now this is sort of like the origin of polar coordinates because the coefficient of dt squared is going to 0, but it's also sort of not like it because we didn't have just in polar coordinates with dr squared. Here we have dr squared by d alpha squared by alpha, but of course that you can get rid of by further coordinate redefinition. So suppose square root alpha is equal to r. Suppose we define r is equal to square root alpha, okay, times some number a, which we'll fix by and by. Now we'll plug this in. So this now becomes r squared by a squared. No, by a. By a squared. R squared by a squared dte squared plus beta squared by now d square root alpha is 1 by 2 alpha. We have to set alpha is equal to r squared by a squared. So this is 2 r dr squared, and then we'll get a factor of a squared, and that will cancel with this, and then there's an r squared, right? So that will be r squared d t e squared by a squared plus four beta squared dr squared by a squared. Is this right?
How did we get 1 minus beta by r equals alpha?
We went to lowest order. Let's do it. So r is equal to 1 minus alpha, 1 plus alpha into beta. So this is 1 minus beta by beta, so that cancels. 1 over 1 plus alpha.
It gives alpha by 1 plus alpha.
But we went into lowest order in alpha. So we keep alpha where it's by itself, but we ignore it in relation to 1. Right? Lowest order in expansion in alpha. We only keep the terms that are really important here, alpha equals 0. Is this clear? Okay. So now this metric here is 1 by a squared, overall doesn't matter for anything. 1 by a squared r squared dt squared plus 4 beta squared dr squared. Let me pull a 4 beta squared out here. We'll get by dte by 2 beta, the whole thing squared. Okay. Now we're in business, because this manifold is only smooth if this coordinate is periodic with periodicity 2 pi. So Te is equal to Te plus 4 pi beta. Beta is 2 is what normal textbooks will call 2m. So that's 8 pi m. Okay. When quantum field theorists go to Euclidean space and make time periodic, they identify the periodicity of time with the inverse temperature. Okay. Just if you want to remember this result, I'm sorry, maybe we shouldn't have gone through this, but let me finish now that we have. We will say 1 by t is equal to 4 pi beta is equal to 8 pi m. Okay. So there is a sense in which, by going to Euclidean space, you might suspect that there is something thermal about the black hole solution, and that you should associate it with the temperature T is equal to 1 by 8 pi m. This is actually correct in a very deep and very important and not completely understood way. Black holes Hawking radiate at this temperature. Okay, but now just to get back to Pranay's question, and why did I say all this? You see, when I analytically continued my manifold, I could only do it in a smooth way if T became periodic. If T became periodic, now let us look at the manifold, the submanifold he was worried about, namely the submanifold R is equal to beta. Pranay was worried that that submanifold looked funny. That is, the span of something and something else was codimension 1 rather than the full codimension. Let's see what happens to the submanifold in Euclidean space. Do you see what happens? Normal submanifolds at some constant value of R are codimension 1 submanifold. Can you see that R is equal to beta, it's a codimension 2 submanifold? Because R is equal to beta is what? So alpha equals 0, R is equal to 0 here. So it's a point in the 2-dimensional space. So it's just a sphere. So you see, under analytic continuation, this is what always happens to these null manifolds. Null manifolds are those manifolds that in Euclidean space would not have been codimension 1 at all. I mean, if you can do the analytic, when you can do the analytic, they would have become codimension 2. This is part of what you're saying in what you're doing. Actually, your question has many interesting answers. The first answer is no problem. It's okay. Okay? But there are many interesting things about your question. But we don't have time to say them all. Okay, but I took the opportunity to tell you about the thermal nature of black holes. Okay, since we started this, and since half of you are experts in quantum field theory anyway, let me just tell you the logic for the association. See, in a quantum field theory, how do we set a quantum field theory at finite temperature? What we do, as we described, is work with the path integral of the quantum field theory with time periodically identified, and the size of the thermal circle is identified with 1 by temperature. That's the rule. Where does that rule come from? It comes from analyzing what it means to do trace e to the power minus beta h in path integral language. The same Feynman prescription that takes time evolution quantum mechanics to an ordinary path integral takes this thing to what's called a Euclidean path integral in Euclidean space with periodically identified time. It's a simple kinematical thing, nothing very deep about it. Okay, but if you've never seen this before, you can read about it. And for instance, there's a beautiful book by a beautiful book called Solitons and Instantons by Rajaram. right, Rajaram. Okay, it's a beautiful chapter explaining this in a way that an undergraduate, or certainly you guys will understand. Okay, but why did I say all this? I said this because this is what you do in quantum field theory. Now you can ask, what is the rule for trying to put a theory of gravity at finite temperature? If we were to try to do the same thing we do in quantum field theory, we would try to put the theory of gravity on a thermal circle. Try to take T and make it go to T, make T identified. However, now there's an inconsistency. The inconsistency is that in gravity, geometry is dynamical. Quantum field theory, you can take a theory and put it on whatever background metric you want. That's up to you. And the field theory will respond. But in gravity, geometry is what is dynamical. So to say I take a gravity theory and put it on a particular manifold is almost like an oxymoron. Then it's not there's no dynamics left. Okay? So what can you do? What you are allowed to do and what you are forced to do when you think about this carefully is, in a theory of gravity, you're allowed to specify the geometry at infinity. So the rule for putting gravitational theories at finite temperature is to go to Euclidean space and look for manifolds that are smooth and with the property that time at infinity is a circle whose periodicity is 1 over your temperature. And then you're supposed to fill in this geometry with any solution of the Euclidean Einstein equations. And what have we found here? We found one way of filling in that geometry with a smooth solution of Euclidean Einstein equation, but only if you choose the black hole beta or mass to be related to the periodicity of the time at infinity in a very particular way. So what we are saying is that if you apply the usual rules of quantum field theory to gravity, and you try to put gravity at finite temperature, you ask what solution dominates this ensemble. You find one candidate solution, namely a Euclideanized black hole, but only if you choose the mass of the black hole to be related to the temperature of the black hole in a way dictated by geometry. Isn't it amazing? This is a first indication that the black hole should be thought of as a thermal object. It was not historically the first. Historically, people came about it in more interesting and more painful ways. But it's the easiest way of saying that a black hole is a thermal object, because it dominates a thermal ensemble, but in a way that is tight. That is, if you fix the temperature, you fix which black hole.
So in the context you just described, the boundary is coupled to a thermal bath. So is it a canonical ensemble description?
You can think of it as a canonical ensemble description, or you can think of it as just computing trace e to the power minus beta h of your theory. In a textbook that might be, people say it's connecting it to a heat bath and so on, but in the end it's a computation of a trace in a well-defined theory. Okay.
What is the trace with respect to what are the states here?
What are the states of the theory? These are the states of quantum gravity, whatever they happen to be. Okay? In some theories we know the answer. The model theories of quantum gravity, till 20 years ago, nobody could answer your question in any theory. 20 years ago, one consistent theory of quantum gravity was found, and the states turned out to be the states of a quantum field theory in some different ways by the area CFT correspondence. So in particular examples I can answer your question very well, but we won't try it in this class. Okay? But if you ask me, in our real universe, nobody knows. This is one of the central mysteries of physics, right? How do you make a good theory of quantum gravity of a universe? That's what you guys have to do, right? Yeah. Okay, great. Let's move on. Any more questions or comments? The last response to your question, let's quickly say this and stop to that, is this, that which should have been my first response because it's more along the lines of the actual question, but anyway, if on an ordinary manifold, if you choose a set of tangent vectors, the basis of tangent vectors at a point, plus the normal, you've got a basis of tangent vectors for all space. Okay? In this thing, there is no natural way in which to take this basis to the basis of all space. And this makes the properties of null manifolds both frustrating and irritating and some very subtle and very nice. So it makes study of null manifolds really different from study of space like triprime manifolds, submanifolds. And we see this in many ways, but later. Okay. Okay, excellent. Let's keep going. Okay, any other questions about black holes before we move to cosmology? So, if you think of Einstein's theory of gravity, it's a fantastic theory in every way. Okay, but just thought of it in terms of phenomena. There are 3 qualitatively new phenomena, broadly speaking, that it has taught us about. One of which is the existence of these fantastic objects called black holes, which we've already studied so far and are becoming experimentally relevant and will no doubt dominate, I have no doubt will dominate 21st century physics from a certain point of view. Okay? There are 2 other phenomena that were not present before, not seriously present before Einstein's theory. First is one of these which we'll study after this one is gravitational waves. The fact that there is dynamics just in empty space. That was not there in any previous theory of, let's say, Newton's theory didn't have that. And that's very interesting. But the last thing, which somehow at a human level is perhaps even more interesting, is that Einstein's theory has made the study of cosmology, the study of the evolution of the universe, part of science. Okay? And it has done it in this completely amazing way that we're going to now start trying to understand. Okay, so we've, in our course so far, what we have done basically so far is analyze souped up versions of the Coulomb potential, right? The Newtonian potential of a point mass. Just analyzing that in Einstein's theory was interesting and led to all cases. Now we're going to turn our attention to analyzing Einstein's equations applied to the whole universe. Okay, amazing, right? Okay. So we're going to do this by making some assumptions. We're going to assume that the universe is isotropic and homogeneous. Isotropic means that in space there is no direction that is preferred. Means you go to a local coordinate system and you will find no distinguished local vector there. No local vector that's different from any other. You can do local rotations in your local coordinate system, all directions are the same. Okay? This would not be true if, there were more galaxies on this side than that side. Because then you could point towards the direction of maximum density of your galaxies. Okay? Somebody sitting here looks in every direction and sees the same thing. Okay? Homogeneous means, say, not only is it same in every given direction at one point, it means that every spatial point is indistinguishable from every other spatial point. Mathematically, this means that there is a killing vector, a killing symmetry that allows you A, to rotate any given little vector at any point to any other direction, and B, to translate any point to any other point on your spatial submanifold. Okay? So this is a statement about killing vectors, or what is technically called isometries of your manifold. It's a statement that's precise enough that you can hand it to mathematicians and ask them, can you classify all homogeneous and isotropic three spatial geometries? And they'll come and give you an answer, and the answer is so intuitive that you'll believe them. Okay? I'm going to give you the result of that kind of analysis, which we won't try to go through. It's not too difficult. Okay. So I'm going to look at spatial three geometries that are homogeneous and isotropic. Okay? One three geometry that is beautifully homogeneous and isotropic, ds squared is flat space. Right? Same in every direction. It's homogeneous. Who can dispute this? Okay. There is another spatial geometry that is homogeneous and isotropic. Okay? And that is this. The locus of points x1 squared plus x2 squared plus x. Consider this. Consider ds. Consider the space ds square, the four-dimensional space, dx1, four-dimensional flat space. And consider the locus of points x1 squared plus x2 squared plus x4 squared. What is the space? It's a 3-sphere. It's a 3-sphere of radius A. Clearly, this is isotropic. Every point on a 3-sphere is the same as every other point. Why? Because each point can be related to any other point by a rotation. Okay. Clearly, it's also homogeneous. Sorry. Clearly, it's homogeneous because each point can be rotated to any other point by rotation. Clearly, it's isotropic because you can choose, choose the north pole around any point, and then do a 2π rotation around that north pole, and that will rotate any axis to any other axis. It's obvious, right? I said this wrong. I said it as if it was a 2-sphere, but it's clear. What I mean is clear, right? It's clearly a homogeneous and isotropic space. Firstly, it's clear that no point on the sphere is special. Secondly, it's clear that no direction on the sphere is special. For instance, suppose it was a 2-sphere, which you can imagine. Then on this point, we can try to draw this arrow, but by a rotation around this axis, we rotate that arrow. And rotations are symmetries.
So at any point, all directions are similar.
All directions are the same. They can be rotated in each other. Firstly, each point can be rotated in every other.
Yes.
And secondly, around any point, every arrow can be rotated in every other. Both statements are true. This is the definition of homogeneity and isotropy. Okay?
Sir, does it mean anything to say that the whole of space-time is isotropic?
Well, isotropic. Yeah. No, I don't think it means anything. Because time and space are just different.
Yeah.
I don't think, unless you can try to give it meaning by some analytic continuation or something like that. That's a good question. Okay. Now, interestingly enough, these two are very intuitive. Okay. Interestingly enough, this does not exhaust the set of homogeneous and isotropic spaces. There is one more, and that is this. Now, do you understand what I mean by this? Do you understand this is a 3-dimensional manifold? How do I get a metric on the 3-dimensional manifold from here? What I do is parameterize this equation by any 3 parameters that solve this equation. And then I plug in that solution into here. Let me do that to be very concrete, just to make sure everyone understands. Okay? One way of doing it is to say, let's suppose x4 is equal to cos chi. And x3, x2, x1 are coordinates on a 2-sphere of radius sin chi. You understand? You understand that this satisfies this equation? Because x3 squared plus x2 squared plus x1 squared is sine square chi. Thank you. Everything needs a name. Thank you. Okay? x3 squared plus x2 squared plus x1 squared is a squared sine square chi. But x4 squared is a squared cos square chi. Okay? And so in this coordinate system, ds squared is now what? All we have to do is to take these expressions and plug them in here. Okay? So let's see what we get. From x4 squared, firstly we'll get a squared outside everything. Then from x4 squared, we will get exactly sine square chi d chi square. Now what will we get from x3 square plus x2 square plus x1 square? You see, this is just like going to polar coordinates in 3 dimensions, except that instead of r, we've used sine chi. So in polar coordinates we get dr squared, so that we'll get d sine chi, the whole thing squared, plus r squared, which is sine square chi, times d theta squared plus sine squared theta d phi squared. Is this clear? But what's d sine chi the whole thing squared? Cos square chi d chi square. And what's sine square chi plus cos square chi? It's 1. So this is equal to a squared d chi squared plus sine squared chi into d theta squared plus sine squared theta d phi square. Is this clear? Okay? So when I say this is what it means. You find some solution of this equation. The solution will have 3 parameters. These are the coordinates on this space. And you plug that solution into here. And thereby get the metric in your coordinates on that space. That's what it means. The people say that this is the metric induced on the manifold from the side. So it's we're looking at the metric induced on the surface by this ambient space. It is obvious that this space has an SO for symmetry, isometry symmetry. This is obvious because you can see it intuitively, right? Just SO4 rotations of this space leave this equation invariant and leave the metric invariant, and so leave the whole space invariant. Okay, great. And this SO4 symmetry you can break up if you like into those things that into an SO3 part that is the homogeneity, and the remaining part that's the isometry. It's not needed. It's the full symmetry. Great. So one space we understand very well. We're familiar with that. It's flat space. Now the second space now we also understand very well. This is a unit 3 sphere of radius a. Let's look at the third space. The third space is the following thing. Consider Consider 4-dimensional Minkowski space. And consider the manifold Let's look first, because this is less familiar first, let's look at it more abstractly than we did for this sphere. What is the symmetry of this space? Well, this metric had an SO3,1 symmetry. And this equation has the same SO3,1 symmetry. So the space will have an SO3,1 symmetry. Okay? As big as SO4. Number of parameters in SO3,1 same as the number of parameters in SO4, 6. Enough to ensure homogeneity isotropy of the final space.
So 4 and
4 into 3 by 2. 6. Yes. Okay. By the way, what is the minimum number of isometries you would need to have homogeneity and isotropy in a 3-dimensional space?
Homogeneity D,
which is in this case 3, and isotropy?
D into D minus 1 by 2.
No, just 2. It's just the unit vectors.
Okay.
The space of unit vectors about a given point. It's 2-dimensional. Number of direct. Minimum number is 5. Here in both cases we have 6. There's one more than you needed to. That's how it works. Okay, great. Now, okay, so firstly the space, whatever it is, has an SO or 3, 1, or 1, 3, whatever, however you write it, isometry. Now, let us try to understand this space. Let us try to understand this space in coordinates in order to see what kind of space it is. It's a bit uncomfortable because we're trying to describe Euclidean spaces. But we looked at a space with a Minkowskian metric. Okay. Now, we're going to get a submanifold of a space with a Minkowski metric that could be either space-like submanifold or a time-like submanifold. Of course, we've chosen a space-like submanifold. Well, that may not be entirely obvious to you. It's basically that this part is bigger than this part. That's what makes it space. That's roughly what makes it space-like. But let's check. Let's check by working it out in coordinates. So what coordinates should we use?
So for the first three, we use the coordinates on 2 sphere times cos hyperbolic, and for the last one, then we could use sine hyperbolic.
Exactly. Exactly. So now I'm clearing this part. Is that okay with everyone? Exactly. So what we're going to do is to write x4 is equal to a cos h sin h. Sin h. I just hope I've got the sign right. Just 1 minute. Just 1 minute. Let me check. Let me take the normal to this manifold. That's xi dxi minus x4 dx4. And now if I compute the norm of the normal, that's xi squared minus x4 squared. Right? So I've got xi squared minus x4 squared. Here this is plus. So the normal is give me a minute. We're working with the conventions minus plus 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 plus. This normal had norm xi squared minus x4 squared, and therefore was positive. But if we wanted a space-like manifold, the normal should be time-like. I may have messed this up. Let me check with that. I think I messed up the sign. Just 1 minute. No, but whether x4 sin h or cos h, shouldn't care about that. Just a minute. If I can find this cell. I think I messed it up. Sorry, but let me check before we run into trouble. I somehow think this should be cos h. It feels wrong. Oh yeah, I'll take longer to find it here, then we'll take to correct it if we may. I think it's minus a squared. I think we want this. Okay, let's go with this, and we'll see as we put into coordinates if we go wrong. I think this sounds right. Okay, so then x3, x2, x1 is equal to a cos h chi. This is sin h chi, h chi, and this is cos theta sin theta sin phi, cos sin theta cos phi. Okay, it's cos phi. The sin. Okay. This clearly solves the equation. Now let's to check that we're right, we have to plug this into this and see what we get for the metric. Yeah, it's working. It's working. So you see how my statement that this is larger than this was wrong. Yeah, it's not where it's larger, it's whether the directions. Anyway, yeah, it's working. So let's see. Now when we plug this into the metric, we get a squared ds squared is equal to a squared minus sine sine h squared chi d chi squared. This is from dx4 squared. And then from the dr squared, it's just like that, what we did before, but we'll get plus cos h squared chi d chi squared plus sine h chi the whole thing squared d theta squared plus sine square theta d phi squared. Is that clear? Same calculation as before. Okay, and we've checked we got it right because cos h squared minus sin h squared is positive. So we got a Euclidean manifold, that's what we wanted. So ds squared into d chi squared plus sin h squared chi d theta squared plus sin squared theta d phi squared. Okay, great. So we finished our theory of homogeneous isotropic three geometries. There are three of these. We understand them completely. Okay, this guy, there was flat space, there was a unit sphere of radius a, and there was the unit negatively curved space, whatever, hyperbolic space is sometimes called. Okay, also of quote unquote radius a. Okay, two more things about these spaces. Firstly, suppose I computed, okay, now I'm going to follow Landau-Lifshitz, who when he's computing curvatures of the three-dimensional submanifold, he uses the symbol P, so as not to confuse with the curvatures of the four-dimensional manifold into which this will eventually be embedded. Okay, so Landau-Lifshitz asks, suppose we ask P alpha, beta, gamma, deltas. What is this? This is equal to what for any of these three spaces? Okay, this is fine. Now, you see, it's got to be some structure built out of the metrics of these spaces. But because everything is homogeneous and isotropic, this has also got to be homogeneous and isotropic. Okay? So the only data that's in our hands that we could use to build this thing is the metric tensor itself. There's nothing else that it could work out to be. Now let's remember the symmetry of this object. This was antisymmetric with respect to this and antisymmetric with respect to this, but symmetric with respect to interchange of pairs. So the index structure must be G alpha gamma, G beta delta minus G alpha delta, G beta gamma times number. Okay, and now I'll leave the computation of the number to you as an exercise. I think it's 6, but let me just check that. Oh, it's 2 and 6 is the other. Yeah. So, yeah, right. So, exercise. Check that this number is 2 by a square. In the case of the sphere, and I suppose minus, yeah, is 2 by a squared for S4. So plus minus 2 by a squared for S4 and H for the S3 and the hyperbola. So positive sign for the S3 and the negative sign for the hyperbola. Okay, next check.
In particular, the derivatives of the matrix don't offer here because it's an isometry, right?
Well, yeah, it's true that there are, yeah, you see, if you had derivatives of the metric, yeah, all derivatives in some sense are 0 because they're all taking you to some other direction. Exactly. Because a derivative would be something that broke the rotational symmetry. Exactly. In an appropriate sense. Nothing else, you try to write down any other structure that you could that is consistent with both homogeneity and isotropy. You'll find you cannot.
Or
Okay?
in other words, the derivatives themselves are linear combinations of.
Exactly. The fact that the killing vector, that there are so many killing vectors, will tell you this. That's exactly right. That's the more precise term. Okay, excellent. So please check that this is the case for the sphere, the hyperboloid, and of course in flat space, p alpha, beta, gamma, delta. The flat case was 0. Yes.
If you raise the indices of gamma and delta, what you get is this epsilon AB, epsilon CD kind of. Can we use that as an argument to say that this can only have this structure?
Say that again, please. Which gamma and delta? This gamma.
And delta. Then what you get here is delta alpha gamma, delta beta delta minus delta alpha delta delta. Okay, on the right hand.
Yes, yes.
So that is epsilon AB times epsilon gamma delta.
Now what is epsilon?
Like Levi-Civita.
Epsilon, but this is a 2-dimensional Levi-Civita in a 3-dimensional space.
Sorry, but there you can use that.
Yeah, no, right. It is true that you might be able to say something special about this being 3-dimensional. However, the argument actually holds in d dimensions. Okay, so these are the set of homogeneous and isotropic space, much more general than any special coincidence of dimensions. And basically the argument that homogeneity and isotropy will force this is just correct always. Okay. Great. So far what we've done is kinematics. Now we want to start doing dynamics. Okay? What we want to do is to write down Einstein's equations for the universe. Now what are Einstein's equations? Okay? Einstein's equations are r mu nu minus half r g mu nu is equal to eight pi, this was g Newton by what is it, 8 pi g Newton by c to the 4. Yeah. Okay, let's write it. C to the 4 t mu nu. But now let us, go back to something that we alluded to right at an early stage in the course. That is, we got Einstein's equations out of the Lagrangian square root g r. But we talked about the possibility of putting something more general here, that is square root g r plus 2 lambda, where lambda is just some constant. So suppose we take this to be the Lagrangian of space-time. Okay? From the point of view of Einstein's equations, you could take this part to be a matter contribution and compute its stress tensor separately. You remember our general principle, you take square root gr plus matter part, and then Einstein's equations are this, where t mu nu is given in terms of the variation with a factor of half or some factor. So I think without a factor, just variation with respect to the metric of that matter part of the Lagrangian. Right? Now, if you want, you can take this to be on the matter part of the Lagrangian, but we're going to keep it as special, single it out as special, because there's no matter associated with it. It's just a constant. Okay? So, in addition to t mu nu matter, we could have what comes from varying this guy. Okay? Now what do we get from variation of this guy? That's just variation of square root g. That gives you a stress tensor proportional to g mu nu. You have to be careful about the factors and the definition of what t mu nu was and so on. And I've chosen all numbers so that this will be plus lambda GV. Okay? So you could either think of lambda as a special, you could absorb this into T mu nu, but we want to keep it special and explicit because it's different. If it's there, it's a constant term, it's not associated with something, doing something, it's just part of, it's really, it should be thought of as part of the theory of gravity itself. No additional degrees of freedom associated. Okay? So this is the Einstein equation that we will try to solve. This is the Einstein equation that will concern us. Now a word about this lambda. This lambda, as we discussed long ago in the course, is an object of dimension 1 by length square. You can see that because R has two derivatives. So it has to have the same, these two terms have to have the same dimension. This is two derivatives of the metric. Metric is dimensionless. So this must have dimension 1 by length square. Okay? And in solar system scale experiments, for instance, there's absolutely no evidence for anything like this. When we solve for the Schwarzschild geometry, we didn't solve this equation. No, we could have. Actually, it's possible to solve that equation. But we didn't solve that. We solved the equation with lambda equals 0. This is because we were interested in black holes of small sizes, let's say solar system scale sizes. However, there appears to be reasonable evidence that lambda is actually not 0, except that the length scale associated with lambda is approximately of order 13.6 billion light years, the size of the universe. Okay? So this is 1 over some huge length scale, and only plays any role, only ever competes with this or this when we are interested in length scales of order the size of the universe. So in almost no other context other than cosmology is the question of, for practical purposes, the question of whether lambda is present or not important. So when we study the Schwarzschild geometry, we ignored it. Okay? But in the study of cosmology, we are precisely interested in length scales of order 13.6 billion light years. So we should not ignore it. Okay? So this is the system of equations we're going to study. But of course, before we study this system of equations, we need to address what is this. This is the thing about Einstein's equations. The part that is geometry is really beautiful, but the right-hand side is left up to you. It's T mu nu. What is T mu nu? It's something. Well, of course, it's because Einstein's equations are incomplete. They talk only about the gravitational sector of the universe. The universe is more than gravity. If all that there was in the universe was gravity plus electromagnetism, we would know what this was. This would be the T mu nu for the electromagnetic field that you guys worked out sometime. But the universe is a very complicated place. Okay? So what do we want to put for this T mu nu here? And now, unlike in the case of cosmology, unlike in the case of the study of black hole physics, where this was just 0, so there was nothing ugly about what we're going to do, what we did. We're going to do something which, is basically okay, but it's a bit ugly. And that ugly thing is to do phenomenology, by which I mean, we say we can't describe things exactly. So let's make a rough model that will get many features right. Okay? So let us assume that on the length scale of the universe, we can think of the T mu nu as the T mu nu as the stress tensor of a fluid with some equation of state. Now, let us think about, before we start doing this, let us think about this a little bit. What does the universe actually consist of? There are all these galaxies, and then there's light flashing around the universe. There may be more things like neutrinos going around the universe. It's a complicated place with all these things. These are the things that the universe consists of. There's no mystical fluid floating around the universe as far as we can tell. We're not claiming that there really is. What we are saying is that we do not want to put in the position of every galaxy. in our equations. If we did that, we will find the equations very hard to solve, and certainly all this homogeneity and isotropy will go out of the window. Okay? We do not want to keep track of every photon of light. That's what we would have to do at a fundamental level. Okay? So what we will do is work with some sort of average, a little like working with trying to describe air in this room. We talk in terms of pressure and density, even though the underlying description is in terms of something else. Here it's coarser, the underlying description in terms of galaxies and stars, blah, blah, blah. But the hope is that we're not going to get things too wrong by effectively thinking of things in terms of some fluid. There may be many components of the fluid. Sometimes they will thermally equilibrate with each other, sometimes only within themselves. All that is a matter of detail, which we will have to think through, understanding the dynamics of all various processes in the universe. Okay? So we will not make very strong assumptions about what this fluid is, but imagine there's some sort of fluid at play. Okay. Okay, we'll come back to what we can say about the stress tensor in 2 minutes. First, now let us write down the metric of spacetime. So we've assumed that spatial slices are gamma ij, where gamma ij, one of these constant isotropic homogeneous spaces, which are either positive curvature, negative curvature, or zero curvature. Okay? So now what's the full metric of spacetime? Well, we need a time-like coordinate, let's say t. So we'll get some gtt dt squared. Most generally we get some gti dxi dt plus something times gamma ij dxi dxj, where I'm using schematic notation. I and j are coordinates. Minus should not be there. Okay. Thank you. GTT will then be negative. Fine. Okay. Where I and j are just schematics for coordinates on the spatial manifold. It's constant negative curvature. We know what this is, right? We've spent some time studying what this is in the 3 separate cases. However, we were going to insist that our universe maintains the isometries of homogeneity and isotropy on the spatial submanifold. What can we say from that about GTI? It's 0, because from the point of view of the spatial manifold, it's a vector. And if GTI was non-zero, it would break, isotropy, because there would be a direction it would point at. Not allowed. Okay, so we've got GTT and A. These are scalars, that's fine. What can we say about the spatial dependence of GTT? No spatial dependence. Why? Because if there was spatial dependence, then it would mean that one point was different from the other. Homogeneity. So GTT and A, both are functions only of time. GTT is a function of time, and A is a function of time.
A could also be a function of x, I know.
No, it couldn't be a function of x, because then the metric would no longer be homogeneous.
Okay.
Because the new spatial metric would be A times
Yeah.
gamma. Okay? Now,
But it would still be, that would be a conformal factor, but the exact homogeneity would be broken.
yes. We don't want just conformal homogeneity, we want homogeneity. Okay. Now, so far we haven't said anything about what our t coordinate is, and it's sometimes convenient. There are two choices of t that are sometimes convenient. A, to make this whole thing d tau squared. ds squared is equal to minus d tau squared. Make a coordinate change, so this becomes d tau squared. Minus d tau squared plus a of tau, maybe this is, I call it little a squared of tau. Gamma ij dxi dxj. This is one choice that's often convenient. Another choice that's often convenient is to work in what is so-called conformal time, which is not to make this equal to 1, but to make it equal to whatever this is. Okay, so is equal to a squared of t conformal, let's say tc minus dtc squared plus gamma ij dx I dx. This gamma ij will be taken to be the unit radius space. In flat space is just flat, but if it's a sphere or a hyperboloid, it will be gamma ij of unit radius sphere and unit radius hyperboloid. So this A is the local radius of the sphere, a local radius of the hyperboloid, which is a function of time. Okay, A continues to be the local radius of the sphere. Whatever sits behind the gamma ij is the local radius of the sphere. It's the same thing here, except now it's a function of a different variable. It's a function of this tc variable. Do you understand? Is it clear that we could go to either of these coordinates? Just a coordinate change between the two. Okay? For different purposes, different coordinates are useful. Landau-Lifshitz works mainly with this guy, but in modern cosmology, often this is employed for various purposes. Yeah, we'll see that as well. Okay? Fine. Please. Why is gamma ij not a function of time? Because there's one function of time. We've chosen this was a function of time, and this was a function of time. So gamma ij is the unit radius metric on the 3 scale. It's by definition not a function. Right? And then we choose a function of time so that these two are the same. We do a time reparametrization so these two are the same. And then we pull it out. Is this clear? Okay. So now we want to start. Now that we've got our equation, we've got our space. We're almost ready to get down to business, except for one thing. I have to tell you a little bit about this team union business. So what can we say about T mu nu? T mu nu, firstly, what is its structure going to be? Ti will be 0 because that would break I circle. Just like for the metric, we will have TTT and Tij. But Tij will have to be proportional to T times gamma I. And TTT will have to be something. Okay? Both this, I'll use tau for now, but it could have been TE, that doesn't matter. Are functions only of tau. Now this is, the unsatisfactory part. This is some phenomenological fluid, and this effective fluid has these properties. If we were dealing with some known theory, we'd have to use the equation of motion of that theory. What will replace using that, knowing that, is this. Now, firstly, what if this was a fluid? What is the physical interpretation of this?
Energy density.
It's the energy density, exactly. Okay, in this coordinate, it's literally the local rest frame energy density in a rest frame that is moving along the tau direction, staying fixed in this manifold. Okay, and what is the interpretation of this guy? It's the pressure. So, to complete the equations of motion, we will need, how does fluid dynamics work? Fluid dynamics works by specifying the stress tensor of a fluid. In the perfect fluid limit, you specify its stress tensor very much like this. And then the equations of motion of the fluid are conservation of the stress tensor. That gives you a closed system of equations provided you have in addition an equation of state. An equation of state is a relationship that tells you what the pressure is in terms of the energy density. Okay, so we will need in addition some equation of state, some relationship between P and epsilon to complete our system of equations. We will leave that as free as we can at the moment, so as to allow various different scenarios. Okay, so this is what we're going to assume for our stress tensor. We will work in terms of an arbitrary P, an arbitrary epsilon. In order to get closed equations, we'll need more information, but we'll do that when we get there. Okay, now we're really in business. Now we have everything we need to know. We can set up our equations of cosmology. Okay, so let's do that. Fine. So what we want to do is to set up the equations of cosmology, which are Einstein's equations. So first, let's try to see which equations are going to be non-trivial. Okay, so we've got Einstein's equations. So E mu nu is equal to 8 pi g by c to the 4 t mu nu plus lambda g mu nu. Okay, so now we've got clearly three kinds of equations. What about I and 0? That's 0 because symmetry will force it to be 0. With all these assumptions, no matter what we do, we'll always get 0. 0 and 0 will be something non-zero. Okay, so we've got a 0, 0 equation. We've got one more equation. What could it be? Exactly. The ij equation, Eij, will automatically be proportional to gamma ij times some E. So there's one more equation of motion. So let's call these E00 and E. So we've got two independent equations of motion. Okay? We've got two independent equations of motion. Now, these two independent equations of motion are for how many variables? 8 tau. So you might at first think that it's like the Schwarzschild geometry equation, and indeed it is. Okay, that if you think of this as if epsilon and p are thought of as some given functions.
The equation of state.
If epsilon and t are thought of as some given functions, then indeed we have one variable and two equations. There has to be one constraint equation relating the two. Okay? What is the constraint equation? Can somebody tell me? Bianchi identity with which free index? E mu t. Exactly. Anything else would have to vanish because it would be a vector, and there are no vectors. Okay, so there's one constraint relating the two of these.
Sir, can you explain the last slide?
This last line? You see, if the stress tensor is conserved, then this thing here is an identity. This is the Bianchi identity. Let me say it. You take Einstein's equations. D mu E mu nu is equal to 0. This was a relationship we proved from geometry. Okay? This is of course always true, but it imposes some constraint between these two equations, these two non-trivial equations. Just like you did in the problem that you guys solved for Schwarzschild geometry. Is this clear or not? If it's not clear, tell me. Let me say it again. Okay? We know that if you evaluate E mu nu, the only things that are non-zero are E00 and Eij like this. Okay? So let's evaluate this object. Let's first evaluate it with free index I and see what we get. Okay? We will get d mu E mu I is equal to 0. Okay? Now this d mu, okay, This d mu can be either d0 or dj. If it's d0, it's 0 because E0I was 0. Should be a bit careful about that.
Yeah,
because of the Christoffel symbols. Yeah, okay, it does. I won't even go into such detail. This whole thing here is a vector, and so will just vanish. On the other hand, let's look at this guy, the guy with the free index 0. Okay, this is d0 E0I 0 0. You know, we have to take this carefully. Okay, plus d I EI0 is equal to 0. Now let's work about all these terms out. This guy here has a time derivative plus a Christoffel symbol. Okay, so the time derivative will give us del 0 E0 0, and then plus we will get gamma m gamma just a minute. Gamma.
Raise the index of the covariant derivative.
Right. Right.
So gamma should be dotted with a G.
Right. Right. Just a minute. Yeah, right. So let's write it as, if you don't mind, I'll just write it with lower and upper. So del 0 E 0 0. Let's get this guy. Okay. So this is equal to del 0 E 0 0 plus gamma 0 0 m e m 0 right plus gamma they're the same term because they're both 0. That's right. Okay, now this guy is whatever it is. It's time derivative of the E0 0. This guy, this m runs over both 0 and I. When it runs over I, we get 0 because EI0 was 0. When it runs over 0, we have to check with gamma 0 0 0s. If that is non-zero, and in this case, will it be non-zero? It will be because, no. In this case, it will be 0 in this coordinate system because G00 is not a function of t. So gamma 0 0 0 is just 0. So in this case, this will just be this equation. I hope I've done that. You have to check it more seriously. But I think you'll just get this kind of equation.
Del I EI 0. So is that 0?
Where?
Del I EI 0. Okay.
Oh, yeah. But wait, right. You're right. But what about the question was what about del I EI 0? But his question was what about the Christoffel symbol? Okay. So the question was what about when we get either this guy becomes a 0 or this guy becomes an I. It's true. You have to do that more carefully. Okay. I'm not going to try to work it out here, but you will get terms from both of these potentially, maybe some of them 0. You'll get something which is, thank you. You get something which is del 0 of E0 0 is related to, do you see what I'm saying? Shall I write down one or two terms here? Please. Okay. Let's do the terms where the Christoffel symbol hits this guy. Okay. EI0 as was commented was 0, but what about the guy where this one is 0? We'll get E0 0. Then this 0 will contract with the 0 of the of this, and then we'll get II. So one of the terms here, the one where the Christoffel symbol has to do with this index, is this quantity here. Okay. The other term is where okay, this guy is non-zero because GII depends on T. So you'd have to work out this Christoffel symbol and we'll get something non-zero. Okay. Then you'll get one more term here, as you said, when we work out the Christoffel symbol from here and here. That will be the Christoffel symbol where this guy becomes a J. So that will have the Christoffel symbol I, J, and 0. Now, once again, where I and j are equal, or this whole thing is proportional to gamma I j.
Small gamma I.
Yeah. This thing is non-zero because this thing depends on t. Okay. This guy was proportional to E0, 0, and this guy was proportional to Eij. Okay. So you'll get some relationship between del 0 of E0, 0, which was del 0 of this part, a constant times E0, 0, and a constant times E. I think we called it E. E. I can't remember. Where? Ha, E. You understand? So these objects that you would think of as independent of each other actually are not independent, just like we saw in the Schwarzschild geometry. Okay, so we'll get some constraint equation between these various EIs. Now, this equation is an identity provided the whole right-hand side is conserved. The right-hand, this part is automatically conserved. Why? Because the metric tensor is covariantly conserved automatically. This part should be conserved, otherwise Einstein's equations are not consistent. But is it conserved? Well, we haven't yet put in that it's conserved. Okay? We haven't yet put in that it's conserved. The conservation is that the fluid will obey the fluid equation of motion. So conservation of that stress tensor is the fluid equation of motion. Okay? So provided this fluid equation of motion is true, this thing would be a constraint. On the other hand, the way we're going to get this business is the fluid equation of motion. Okay? So, the two Einstein equations have exactly as much information in them as, let's say, one of the Einstein equations and conservation of the matter fluid stress tensor. Okay? So we already know now with the Schwarzschild geometry that we could work. So there are three separate equations that we could write down. There's the 0, 0 Einstein equation, there's the Ij Einstein equation, and there's the conservation of the matter stress tensor. These are not all three linearly independent. This analysis showed us that if you assume conservation of the stress tensor, then there is a linear relationship between the two Einstein equations. So in other words, there's a linear relationship between between derivatives of the two Einstein equations and conservation of the stress tensor. So the three equations that you might write down, only two are independent. Okay? This time I'm not going to make you work so hard. I'm not going to ask you to write them, to check all this, though anyone who likes to should go ahead. We'll just choose two convenient equations, reassured that it's all making sense because it made sense for the Schwarzschild case. Okay? And solve those. Okay? The equations we're going to solve, that we're going to set up are the 0, 0 Einstein equation, and we will use conservation of the stress tensor. The third equation will be automatic from this data. Maybe at an appropriate point I'll ask you to check that. But okay, that's what we're going to do. So we've got this system of equations, this setup, and all we have to do is to find the 0, 0 component of Einstein's equations, process the conservation of the stress tensor. We have our equations of the universe. Okay, it's pretty good. Okay, now we'll stop this class now. Can I have a volunteer to work out the 0, 0 Einstein equation? Another volunteer to work out conservation of the stress tensor. briefly, 5-10 minutes next class. Somebody who's not volunteered so far. I won't force. I mean, so nobody volunteers, I'll do it, but it's good for you. It makes sure you will. Nobody? I mean, come on. It's not hard. You'll do one. Which one? E00. Okay, great. So we've got the harder one. Conservation of the stress tensors. Piece of cake. Conservation of the stress tensor. Okay. Okay, I'll do the conservation of the stress tensor. Okay. So we'll work out, next class we'll work out the algebra. It's very simple stuff. It's really very easy. Okay, I mean it's not really. Sometimes it's hard to keep factors of 2 or minus signs, but with the help of the class it's no problem. Okay, yeah, so we'll work that out and then we'll try to understand the physics of what we've done.